So last class, we reminded you about oxidation numbers and identifying what was oxidized and what was reduced. So for example, again, it might seem a little odd, but the equation up on the board, which is the number 1 on that worksheet that you have, again, besides chromium in a normal state of 0, all the oxidation numbers are there for us already. Went over identifying how to tell if something was oxidized or something was reduced. Remember, if you're reduced, you gain electrons, or your oxidation number gets smaller. It's reduced. To be oxidized means you lose electrons, or your oxidation number gets larger. So if I look for reduced, I would say that the tin plus 4 is the thing that was reduced. And oxidized, I would say that the chromium. Now, if you want to put the 0 up there, sometimes it's nice to keep track of it. You can. Would be the thing that's oxidized. Okay, are we okay with that to start with? Remember, the oxidation number gets bigger, it's oxidized. If the oxidation number gets reduced, it was reduced. What we have to introduce today, then, is taking this a step further. And that step further that we're going to do is we're going to start to write what's called half reactions. In other words, if chromium starts as a 0, it became chromium 3+. Now, to become chromium 3+, it must have lost electrons. After all, Leo goes Ger, lose electrons, oxidized. So we know on the product end, there's a loss of electrons as well. In a redox half reaction, the charges on the left and the right side of the arrow should balance out. In other words, we should know how many electrons were lost by that original chromium in order to create the 3+ ion. How many electrons were lost? 3. This right here would be the oxidation half reaction. Now again, I know that worksheet that you have, they're all bunched together. Boy, when we start working a little bit, you look at my answer key, all I do is write off to the side this type of stuff. Reduction. Reduction means you gain electrons. Remember, Leo goes Ger, gain electrons reduced. So it's going to gain electrons to become the tin plus 2. Well, how many electrons did it gain? Doing a little math here, that would be 2. This would be the reduction half reaction. So this is the first new little tweak that we have to introduce to you guys. Not only identifying what was oxidized and what was reduced, but we can write these small half reactions. Last thing I want to bring up, last new thing I want to go over kind of for today with redox, because again, we have to take it a step further next class still, is notice how the electrons gained does not equal the electrons lost. That doesn't make sense. Conservation of mass, how can we be losing more than we're gaining? The two should be balanced out. And redox chemistry is very common, and I'll just extend the page to show this up a little bit higher for you guys. It's very common to write what's called a net half reaction. We're going to combine the two. But in combining the two, we have to make sure our numbers of electrons lost and gained equal each other out. And I would compare this almost similar to in a math class where you have two equations that have y and x both in them, and then you have to try to cancel things out. Well, I can multiply the first one by this and the second one by that, and then add them together. We can do a similar thing here, where if I multiply this first equation by 3 and the second one by 2, that means I would have 6 electrons gained and 6 electrons lost. They cancel each other out. Just like in an algebra class where two variables, 3x plus 4y equals 16, and then y plus x equals 12. I have no idea if that works out. You could cancel out variables when you add them together and you multiply by different factors. We want to cancel out the electrons gained and lost. And then we can combine this equation. And in doing so, I would have 3 of the Sn plus 4. Plus, I don't have to write my 6 electrons because those are going to cancel out with these. But my other reactant would be 2 of the Cr, making 3 of the Sn2 plus 2 of the Cr3 plus. A net redox equation should abide by conservation of mass in that the same number of each element is on each side of the arrow. 3 tins on the left side, 3 on the right, 2 chromiums on the right, and on the left. That looks good. It should also abide by conservation of charge, if you will. Where if I have 3 plus 4s on the reactant side, that's a total of a positive 12 charge. I do have a positive 12 on the right-hand side as well. Why we go over this is for a couple of reasons. One, within a lot of solution stoichiometry, we get rid of spectator ions. They don't do anything, so who cares about them? And you can even see that with the original equation up on the top of the board, that it didn't include like nitrate or whatever else was involved. So it seems more complicated early on to deal with equations with charges, but we're simplifying because we're getting rid of all the things that don't do anything. Secondly, again, end of the hour, we have to go over titration math. And as I mentioned to start class, we're going to do a redox titration at the end of this week and beginning of next week. We can use these coefficients in stoichiometry. And now we don't have to worry about balancing out equations with all the other stuff. We only have to focus on the things that actually change. So that's the benefit of this type of equation. I'd like to go over one more with you guys and then give you a little bit of time to work on this. All right? So, second one. Second one is probably aluminum reacting with an acid, because H plus is typically the symbol used for an acid. And that will give us Al3 plus. Other reason why I'm fairly sure it's dealing with an acid is it creates hydrogen gas, and metals in an acid usually create hydrogen gas. Things that stand alone are a 0 for an oxidation number. So I know those already. It doesn't matter what order you figure out what was oxidized and what was reduced. In the previous problem I figured out reduced and oxidized. I can do the exact opposite here. Whatever was oxidized had its oxidation number increase. So was it the aluminum or the hydrogen ion that was oxidized? Which one? The aluminum. Aluminum, 0, became aluminum plus 3 electrons. Again, the reason why I know it was 3 electrons is that way the charges balance out on both sides of the equation. Which means the hydrogen ion must have been reduced. To be reduced means you gain electrons. Among other things, notice how in the oxidation equation, the electrons are always on the product side. In reduction, they're on the reactant side because you're gaining them. Here's the next little wrinkle I have to put into this problem. A diatomic, we're not going to split up. We're going to keep it as H2. So don't just call it H. Again, I'm trying to go simple to more complicated instead of straight into full blown. This is all of it. So this is one of the steps that we need to take to do that. Again, next class we'll take the next step a little bit further from this still. But to balance my reduction equation then, I first have to identify that I have 2 hydrogens on the product side. I need to put a coefficient 2 in front of my H plus on the reactant side to balance out my number of hydrogens. Then to balance out the charge, I need to have 2 electrons there as well. And again, if I now combine these two, what should I multiply the oxidation equation by? 2. Reduction, what should I multiply by? Spangler's giving me 3. I don't know if she was actually doing that on purpose or just it's in her head, but it worked. So, if I do 2 times that, there's 2Al, plus I now have 6H+. Those are my 2 reactants. Remember, every time electrons will cancel out for this. I have 2Al plus 3 and 3H2. When I looked at WebAssign for tonight, at first I thought it was going to be complicated because I thought you were going to have to type out the entire equation. I must have got rid of that. And all I do is have a couple of problems where there's a blank in front of each thing. And you have to fill in that blank with what's the coefficient that should go in place for that. So you're balancing the redox equation. Now, to keep things simple, when you look at a question like number 4, for example, I bet the nitrogen in NO3 is going to change from the nitrate polyatomic ion nitrogen to the nitrogen dioxide one afterwards. Why don't you just figure out the nitrogen part? So nitrogen goes from here to become something else. So in other words, pick individual atoms or ions when you do your oxidation and reduction for today. The one exception being I want you to represent diatomics. You will learn next time that it's not as simple as that, and we will take it a step further. But I kind of like to do this one step at a time, where last class we learned how to identify what was oxidized and reduced. Quite frankly, a review from Chem 1. Today we learned how to write an oxidation equation like I did up on the board, the aluminum becoming aluminum 3+ plus 3 electrons. We learned how to write a reduction equation, and we learned how to combine the 2 together. That combine the 2 together is what's going to be helpful for us later on when we do stoichiometry. So for today,